बड़ा फ्लैट छोटे बड़े ये सब करते रहे उस साइड में कुछ कर लेंगे।
I don't need to turn this on, right? No. This is it's. So when you look at surface and interface phenomena, you have to consider these interfacial energies and the angle of contact for all real systems. The problem is that there are many factors that can affect the spreading of liquids or interaction of solid and liquid. For example, the chemical inhomogeneity. So when you have, for example, steel, ordinary steel, plain carbon steel, you have on the surface, you may have a region of pearlite, ferrite, austenite. So different chemical phases, how each of them will interact with the liquid is going to be a critical factor. So chemical inhomogeneity could affect interface. Surface roughness or any machining marks on the surface will affect the spreading of the liquid. Also, when you have a process like a dip coating process, the liquid may climb up or it may be depressed. Now, interestingly, when you have a melting process, when you select a crucible material for your melting process, you want to have this kind of a behavior. The liquid should not spread on the crucible material because you want to minimize the contact and minimize interactions and contamination. But on the other hand, when you want to make a bond, like in joining or compositing, you want the liquid to spread on the fiber or the solid. So depending on your practical needs, you may or may not want spreading of a liquid on a solid. So again, we'll not go too much into fundamentals here, but the whole idea is that things like the roughness of the substrate, chemical inhomogeneity, all those things can affect how a liquid will interact and spread on a solid surface. There could also be uneven spreading because of roughness. So this is a carbon-carbon composite on which we have a metallic droplet, and it did not spread uniformly. You can see the shape is not spherical. It is anisotropic. There are other problems that take place when you look at high temperature systems and when you look at interaction between liquids and solids. For example, you may have some partial infiltration of open pores. So this is the liquid droplet that was sitting on a substrate with some porosity in it, and the liquid is able to penetrate and fill up the pores inside. Or there could be chemical reactions between the liquid and the solid. So this is the solid region here, aluminum oxide. This is the liquid containing titanium, and titanium reacted and formed a reaction layer in addition to infiltration. So the bottom line is that when you look at high temperature interactions between solids and liquids, there could be many things happening that don't happen in low temperature systems. Water or liquid, organic liquids, they don't have those kind of challenges. So I'm looking at high temperature systems that are of importance. I'm going to skip some of the slides here because it won't be very interesting to go over the theory here. But the point is that you can use basic fluid dynamics to predict the rate of infiltration of any pores. For example, how these pores will be infiltrated in terms of a fluid dynamic equation. So maybe I'll skip this one and the next one here. So how do you characterize the wettability of liquids on a solid surface? If you take a drop of water and put it on the surface of a glass plate, or take a drop of mercury and put it on a glass surface, you can measure the angle of contact very easily using a commercially available goniometer or a machine that can take a good image of the droplet and then it can do a curve fitting to give you the angle of contact. That is fine, but when you get into high temperature systems, metals and other solids, it's a very complex thing. So this is a system for wettability measurements at very high temperatures. This was actually designed and built by one of my colleagues in Poland, Dr. Natalia Sobczak. She's the vice president of the Polish Academy of Sciences right now. The whole problem here is that you have to have capability for very high temperatures, isothermal conditions, under very high vacuum. 10 to the power -7 torr. And you should be able to manipulate the liquid inside the chamber so that you can do a variety of things. So I used some of this kind of an approach to study wettability and interfacial phenomena at high temperatures. So we'll look at some of that today. So when you put a drop of aluminum on a carbon substrate, either for joining purpose, soldering, or for making a composite of aluminum and carbon, you run into issues like this. Aluminum will immediately react with carbon and form aluminum carbide, and that is not a smooth layer. That is going to make the surface rough. And the reaction is taking place even ahead of the liquid. So when the aluminum is spreading, it is not really spreading on the carbon, it is spreading on the aluminum carbide surface. It is already rough. Another example, when you have nickel aluminide liquid on a magnesium oxide substrate, there is chemical reaction and you form a compound, a spinel compound that forms like whiskers. So now when this liquid is spreading, there will be some resistance because of the whiskering on the surface. In aluminum silica, quartz, if you put a little drop of aluminum on quartz, there will be spreading and reaction and also some cracking. So liquid will be infiltrating through that crack. So these kind of phenomena don't take place in low temperature systems, in organic liquids on a solid surface or water on a solid surface. But when you deal with high temperature systems that are important for manufacturing of materials, then you run into all these kind of important problems. Another problem that takes place at high temperature is that liquids evaporate and condense under certain conditions. So in this example, I'm looking at a nickel droplet that is on a aluminum oxide substrate, which had a coating of chromium. So we had a chromium CVD coating on the aluminum oxide substrate. Then we put a solid nickel piece under high vacuum and we melted it. So even before the liquid spread, it evaporated and condensed and modified the surface ahead of the droplet. In other words, the droplet is not spreading on the original surface, but it is spreading on a modified surface. And then you can do all the chemical analysis and identify what phases are forming. But the main takeaway here is that at high temperatures, interactions can take place through the vapor phase, through the solid phase, along the surface. So the surface is continuously getting modified. Here is a video. I think you can see the video here. This is just a little droplet, 2 or 3 millimeter diameter droplet of a nickel phosphorus on aluminum oxide. I'm sorry, this is aluminum droplet on aluminum oxide. You can see how it spreads under high vacuum. This is a high speed photography. Now look at the same thing when you have an oxide skin on the surface. You can continue here. You see, this is a very teeny droplet, but because the surface has the thin oxide skin, the metal is melting underneath and spreading out. So this skin oxide has not broken up. And remember, this is under very high vacuum. Even under very high vacuum, you have an oxide skin on this little droplet that is preventing spreading of the liquid. So these kind of challenges occur in real systems at high temperatures. And again, as I mentioned, this is happening under high vacuum. So even though you have good vacuum, it's very difficult to get rid of all the oxide. And because of that, the spreading the liquid will be difficult. Now, if you have very high temperatures, then this little solid piece, which has oxide on it, that oxide will begin to dissociate at high temperatures. So I think my video is working. You will see that as this melts, the oxide will actually break up. Sure, if it is. Maybe it's not running the video here. Sure, let me see if I can run it this way here. You see the droplet has spread, I mean, it has melted, and you will see little oxide skin that broke off. So these kind of effects are quite challenging to handle at high temperatures. Am I okay with this? Or did I? Okay, I will not go back again. I think the video was not running, so I just came out. So maybe you can just
we'll just duplicate the screen. Actually, what is happening? Your screen is getting visible there, so we'll just duplicate the slideshow.
Okay, but the video is not running on this. So okay, now it's running. Okay, thank you. All right. So again, the droplet, you see the oxide little broke off, and now this is a much cleaner aluminum metal. So in real practice, if you have aluminum in contact, molten aluminum in contact with an, let's say, aluminum oxide crucible, you will think that there is no spreading possible because of oxide on aluminum. But in reality, if you can get rid of the oxide, then aluminum will spread very well on an aluminum oxide surface. So if you look at all the literature data on spreading of aluminum on aluminum oxide surface, you will see a lot of scatter. The numbers are all over the place. There is really no trend except that at high temperature, the contact angle decreases, which means spreading becomes easier. So this kind of a behavior is both good and bad. It is bad from a practical point of view because you don't know whether the liquid is going to spread or not. Contact angle is unknown because of scatter. But the good thing is that because contact angle is extremely sensitive to surface preparation and surface conditions, measuring contact angle can be a high fidelity probe to study the surface and interface phenomena. And that is what we attempted to do. And again, this is showing you how a little drop of aluminum, molten aluminum, that was put on aluminum oxide, silicon, how the droplet behaved at different temperatures. So as temperature increased, the angle of contact decreased, but it was always above 90 degrees up to 1000 Celsius. At 1000 Celsius, the contact angle came down below 90 degrees for all three substrates. And that was because the oxide on the droplet broke off, it dissociated, and that's why the liquid was able to spread. What does that spreading behavior have to do with the between the solid and the liquid? So we did some experiments where we first did this side drop experiment where you allow the droplet to spread under high vacuum isothermally. And then after measuring the contact angle, you solidify the droplet on the substrate. Then you bisect it, precision cut it, and then conduct a shear test to dislodge this droplet and measure the bond strength. So you plot the shear stress as a function of the displacement of the droplet. And these are the data for aluminum in contact with titanium oxide, shear stress data, and these are the corresponding data for contact angle. And we see that lower the contact angle, higher is the bond strength. If you can remove the oxide skin on the solid, on the droplet. We see the same kind of behavior for aluminum, zirconia, and other ceramic materials. So in the traditional test for studying interface and surfaces, we start with a solid sample of a metal. We place it on a solid surface, could be metal or a ceramic, and we melt it under high vacuum. Once the solid has melted, it will attain some equilibrium shape like that. So these are the pictures that you can see for contact heating. Initially, a solid is in contact with the solid surface, and after melting, you have spreading taking place. The problem is that in contact heating, you're not able to control the actual contact time between the liquid and the solid, because the solid is heated in contact with the substrate. So if you want to really study how liquid interact with the solid, then you want to bring only liquid in contact with the solid, not have the contact heating process. And that is done using what is called a capillary purification method. You heat the solid in a crucible, in a tube like this separately, and heat the substrate separately inside a vacuum chamber. Once the temperatures are reached, the correct temperatures are reached, you squeeze the droplet on the substrate, and then you study its spreading behavior. So these kind of experiments are extremely difficult to perform because you're trying to manipulate a solid and a liquid inside a high vacuum chamber at very high temperatures. So even a slight disturbance, mechanical disturbance inside the chamber could change the behavior. So that is the reason we have very complex experimental setup. But the main benefit here is that you are able to study interaction between liquid and solid directly without having to worry about this interaction during the solid state. So here is another video of how this experiment is done. You squeeze the liquid out from a little high purity ceramic tube and bring the liquid in contact with the solid and allow it to spread uniformly. And then you can measure the spreading behavior on the solid surface and find the contact angle as a function of time. So these kind of tests are very difficult to do, and only 1 or 2 labs in the world have that facility. This is after the certification, when the droplet is certified. So again, the same thing is shown here. When you remove the droplet from the surface of the substrate, you can actually study what kind of chemical interactions took place between the liquid and the solid. So in this case, aluminum that was in contact with single crystal aluminum oxide. The bottom picture is for in both cases, you some kind of a dissolution reaction behavior, which means you have some new aluminum oxide crystals forming on the original substrate. So in this case, there is no chemical reaction because aluminum will not react with aluminum oxide, but there is still chemical interaction because the aluminum oxide substrate dissolves in the liquid aluminum droplet, and then again it reprecipitates into the new crystals during cooling process. This is another example of how you can remove a droplet after a fixed amount of contact time. So this allows for a more scientific study of the interface. You see how this droplet will be picked up now by everybody. It's going to be sucked up, and this surface is now going to be examined for the things. One of that we do to study interface is droplet pushing. Liquid has melted in contact with the mechanically push the droplet to open up the interface below the liquid. And you can do the chemical analysis and other things. So we call droplet pushing behavior. That is, first you melt the solid in contact with the substrate. Once it has melted, then you push the droplet and open up the interface. So these are the AFM images of the liquid droplet side, and this is the side where you didn't have any liquid in contact with solid. These are different micrometer scale in the droplet. And what we see is that even under that 2 or 3 millimeter diameter droplets, you have little droplets that sit in dislocation edge pits. These are micrometer size droplets that broke off from a bigger droplet, and they sit in dislocation edge pits to create some kind of a structure. So this is how you push the droplet under high vacuum. You're mechanically pushing and opening of the interface, and that is examined for interaction. In some systems, we see that even though wetting is poor, which means the contact angle may not be very low, there is still adhesion or bonding. So this little ceramic substrate was picked up by this solid, even though the angle of contact was not very high between the two. So many alloys show high adhesion to substrates in spite of weak spreading of the liquid. Another example here is how aluminum react with pores. So you can see this reaction zone developing. So what we did was we had this aluminum solid piece, and this is the quartz plate. Silica or quartz is transparent, so you can see from the other side how the chemical reactions are taking place. And you will see that reaction zone forms with time, and then during cooling, some cracking will also take place. When you cut open this system, when you cut the substrate and droplet combination after cooling, you see the reaction layer underneath the solidified droplet. And then we do some chemical analysis and other structural studies. So some of this may not be of direct interest to people here, but these are the kind of experiments one does. Now here you're looking at 3 different quartz plate or 4 different quartz plate over which we placed aluminum, solid aluminum, and then melted it. And you can see how the aluminum is moving through these quartz plates under high vacuum at high temperatures. And when the cooling has taken place, you can see the quench cracks. So from these kind of experiments, we are able to calculate the rate of interaction between liquid and solid. And these kind of things could be of use in melting processes and making composites of aluminum with ceramic materials. Another interesting thing we see is that under vacuum, metal droplets actually kind of begin to dance because there is some gas evolution from the solid or degassing that causes the liquid to kind of bubble up or liquid to kind of jump on the surface here. So you can see right now the droplets melted, stationary, and then it will begin to jump, kind of hop because the gas evolution from the surface here. And mind you, everything is very, very pure in the system. High purity substrate, high purity aluminum, high vacuum, high temperatures. But still, you have some gas evolution. You see the droplet is jumping because underneath you have some degassing taking place here. So these are kind of scientific experiments, but they do provide about surface and interface phenomena in high temperature systems. Metal shrinkage during certification. You see the liquid is in contact with this single crystal plate here, and now it is in contact. When it is cooling, the shrinkage will cause this to be lifted up here. Because good spreading, good welding means there is good bonding, and therefore this plate will be lifted up. Okay, it is reheated, remelted, and let's see here. All right, I think it was. There is change in the volume of solid when it interacts with the liquid. So we are looking at aluminum in contact with a ceramic surface here. And initially the surface is flat, but after melting and after chemical interaction, there is a change in the volume of the solid and the surface become more curved. Okay, I'm not sure if I can you help me? Just I want to run one video here real quick. This one here. Space will do. Just a minute. This is the video here. Just one. Okay, that's. Yeah, I think it's running. So right now, I think the solid is melting, and slowly you will see the flat surface of the solid becoming curved because of chemical reactions, and eventually it will become more curvaceous. I think this is even the last view that I wanted to show. So one reason I should be good. But you can see how the surface of the solid is changing because there is a reaction in the solid, and that's causing any change in the volume. So when changes a little bit because of chemical reaction, and you cause some stresses in the system. This should be good. Okay. Okay. So I had a question here for you. If I finish early on this one, can I continue with the next topic, or will we be break after 1 hour? What do you? Oh, 5 minutes. 5 minutes. Then after 3 hours.
Yeah, that's why it's just like.
Okay. All right. All right. So we'll just continue. So again, when you study interfaces at high temperatures, these complex phenomena take place that we don't encounter in low temperature systems that have been studied very much by chemists and physicists. But when you get into materials, high temperature materials, then you have these new challenges that need to be accounted for. Again, I think I'm thrown out here. I wasn't able to.
Go to next.
Models won't allow me to do that, or enter button. It didn't allow me to.
Does not allow it. So okay.
This before I can start. So. From page up and page down. Oh, with that, not with the enter. No, not with the mouse. No. Okay. All right. That's what I was doing wrong. Sorry. Thank you again. All right. So I'm pretty much close to the finish line for this particular topic here, even though it might be a bit early, so we can have discussion if there is a need. But this is an example of interaction between a silicon nitride and aluminum, pure aluminum, commercially pure aluminum. And what we see here is that, by the way, silicon nitride now is being considered very much for high thermal conductivity applications, because silicon nitride among ceramics has a relatively good thermal conductivity. So when you have silicon nitride substrate for thermal management applications, silicon nitride might have to be bonded to metals or polymers or other materials. So the interaction of silicon nitride with other things, other materials is important. So we are looking at aluminum in contact with silicon nitride, and there is a chemical reaction between these two things. And under the droplet, you see a reaction product region, some cracking, but then the reaction, you started with pure aluminum, and because of reaction, some silicon is released, so the droplet becomes aluminum silicon alloy instead of remaining pure aluminum. So the chemistry keeps changing during the process. Another example of interactions, zinc oxide single crystal was in contact with pure aluminum. So on this side, we have the droplet of pure aluminum, and over here was the solid single crystal zinc oxide. But you can see that it is no longer a single crystal because of reaction of zinc oxide with aluminum. There was dissolution and reprecipitation of aluminum oxide crystals. So these are the newly formed aluminum oxide crystals inside the initial zinc oxide single crystal here. So this is another complexity that plays into system because you had a single crystal here. Now it is no longer single crystal because of the reaction. And you have channels through which the liquid can be wicked, or it can seep through. You have roughness coming into picture. So those things will modify the spreading behavior. So as a summary, overall summary, basically, when you study surfaces and interfaces in high temperature systems, a lot of complicating factors are coming into play. Their reactions, the roughening, composition changes, volumetric changes in the solid, oxidation of the droplet, even under controlled condition. So all of those factors are very difficult to control in real systems. But when you study them scientifically, at least you are able to get some insights into physical processes underlying. So right now, the need is to develop new methods, innovative methods to characterize wettability, reactivity, and interface formation in real systems, because the fundamental science from low temperature systems, that is no longer applicable to high temperature systems here. Even though we still use the same concepts of contact angle and surface energies, they are not applicable to our real systems here. So we need to characterize contact angle evolution in real systems, reaction kinetics, infiltration, and other things, especially in systems that are of interest to industry. And then there is a need to develop and validate models of reactive wetting systems here. So just as a final slide for this topic, we are looking at this conceptual scheme where you have a liquid droplet that was sitting on a solid surface at high temperature under high vacuum. Unlike mercury on glass or water on glass, where you have stabilization taking place in a microsecond, over here, the liquid will keep spreading for an hour or 2 hours because you have chemical reactions driving the spreading. So one situation is that spreading of the liquid is faster than the growth of the reaction layer here. The second possibility is that reaction layer grows faster than the spreading of the liquid. In this case, the liquid spreads not on the original solid, but on the modified surface. Then there could be challenges like cracking or pore formation in the reaction layer. So some of the liquid will penetrate and it will be lost from the surface. So, and you can have in the reaction layer, it may not be just one reaction product. It can be multiple reaction products depending on the systems involved. So these kind of complexities are being studied in high temperature systems. And most of the research that I showed in this was done collaboratively with my colleague in Poland, Dr. Natalia Sobczak. So I just wanted to acknowledge her here. Thank you. So if any questions or discussion points, I'll be happy to handle those. Yeah.